Hi, Christof. Thank you very much for the invitation. What will you show me?
Well, we look at our lab when we do the inverter testing and the arc fault detection testing.
Where's your lab?
Just over there. Please follow me.
Yeah. Christof, where are we here?
We are in the photovoltaic laboratory of the Bern University of Applied Sciences.
We want to talk about fires of PV systems. Are we talking about a real and relevant problem?
Well, that's a good question. So we wanted to know whether fires are a problem, and we actually have offered the Swiss Building Insurances a program to monitor fire for photovoltaic systems. And they said, well, we don't have cases, we're not interested. We said, well, of course you have cases. We know that from the media, from the press. They said, yeah, but they are not relevant. So no, PV fires nowadays, although we have maybe 200,000 PV systems in Switzerland, PV fires are not a problem.
If I'm a house owner and if I want to build a PV system, and even if there's a tiny risk, shouldn't I minimize this risk and make sure that there absolutely is no chance of a PV fire?
Well, of course, there's never zero risk. So there's always risks, and we know there are fires in buildings due to the electrical installation, for example, not necessarily photovoltaic systems. And the most important thing is that you should install PV systems with good quality, which means take good products, make sure that those who do the installations are professionals, that they do proper installation works, and then the risks are really low.
What are the main drivers for the risk? If you read the media, there's plenty of energy storage related risks that are discussed. What about other components?
So the main risks for fires, when there are fires in PV systems, I would say first of all, the main driver are not the PV systems, but the main drivers are fires in buildings where there is a PV system on the rooftop. On the other hand, of course, there are fires which were caused by the PV systems, and now there's really the problem that we don't really know. So fires are so rare that there are no proper statistics, at least not in Switzerland. In Germany, the latest statistics we have, they're about 10 years old, and there we have seen that both product failures and installation failures are certain failures which can occur. And when it comes to products, then it might be connectors, cables, connectors, also inverters, for example, which might cause fire hazards.
You mentioned inverters. Which role actually do inverters play? Can they also prevent fires that are caused by other components?
Actually, they can. So inverters can prevent fires which were caused by other components. For example, if there is a fire caused by a connector, by a bad connection, for example, then this gives a certain mark, so it's harmonics on the electric current, and these harmonics can be detected by the inverter, and the inverter can then interrupt the current and extinguish the cause of the fire.
Christof, how do I know that the inverter I want to buy has a good arc fault detection mechanism?
Well, that's a good question. We wanted to know that too. And the thing is that the inverter manufacturers, they just declare AFCI, so arc fault current interruption, and they claim they have this functionality. We know that it basically works. It is there. And we have tested different inverters, and we have seen with some of them it works straight away. With others, it is declared they have it, but it didn't work at the beginning. And we had to find it, to switch it on, to find the correct parameters. So I would say nowadays, ask the manufacturer, ask your supplier if they have experience with the respective devices, or come to us, to our lab, and we can test it.
So you do these tests at your lab. This is what we see here.
Yeah, so in our lab, that was exactly the question. We knew that new modern inverters, they do have this AFCI, but we didn't know if it really works properly. And there is a specific standard for this arc fault detection, and this standard is 63027, long number, and it basically requires an inverter to detect an arc and to be able to disconnect the cable from the PV system, or to interrupt the cable inside the inverter when such an arc occurs. in our lab. So we did the tests according to this standard to see if this baseline is fulfilled. But we also wanted to do more tests to dig a bit deeper into real problems, into real systems, and see if it also works in the real world and not only in the normative world.
And how did you do that?
So, well, first of all, we built up a PV system. That's what we see with the inverters we have behind us, with cables we have in our lab. We have here a small sample of a cable, which we used to emulate a very long cable. So one of the specific questions was, if a PV system has a very long cable connection, would it still work? And what we did is we set up the PV systems, the modules, the inverters, put a long cable in between, caused an arc by disconnection of a cable. So a typical method to interrupt the arc is actually this ring ball method. So we have a ring, we have a ball, and we just disconnect these two devices, and then we have this arc in between. And the standard requires this mechanism. It's the most difficult arc to detect for an inverter. So therefore the standard requires that. We have also tested with normal loose contacts, for example. We have also tested with connectors. If a connector is opened, if the inverter would still sense the arc in that manner, for example. We have tested with high voltages and with low voltages. We also have tested with high currents and low currents, just to see if certain influences which we see in reality, if they have also an influence on the behavior of the inverter.
And you have tested all the inverters that are available in the market?
Unfortunately, we did not yet test all the inverters which are available on the market. We have tested 3 brands. We see them behind us. So we have tested a Huawei inverter, a SolarEdge inverter, and also an SMA inverter. These were actually the only inverters we could get when we started the tests, which had this arc fault detection functionality activated also for the European version. For the inverters which are sold in America, these functionalities are standard in probably all inverters, because it's required by American standards. In Europe, there are only rumors that this would be required in future. I know, for example, that in the Swiss installation code, it will not be required, also not in the new code, which will become active next year. And therefore, we could only buy a few inverters with these functionalities already activated. And these were these 3 inverters.
Christof, you sound very knowledgeable in this domain. What is your background, actually?
My background is electrical engineering, but all my professional life I have worked with photovoltaic systems.
All this is yours. This is your home. This is where you work. This is where you live. This is where you put all your energy. What are you specialized in?
Well, our laboratory is specialized for applied sciences. So that means that we often test products. We see ourselves somewhere between industry, fundamental research, and then the end users of products. So for example, if a new product comes to the market, the end users might not know what this product is good for, where the weaknesses are, where the strengths are, and such things are being tested in our laboratory.
Very interesting. Can you show me around? Can you give me a lab tour?
Yes, of course. Let's have a look at our devices.
Great. What do we see here?
So here we see the setting for our arc fault detection tests. We have in this box the contact, which we'll open, where we see the arc. We have here an oscilloscope, which shows us the energy, the current, and the voltage of the arc and the time it takes to interrupt it. And this is the laptop which we use to operate the whole system. So I will start now the test. At the moment, there's current flowing through our cable. And when I press the button, then the contacts will open and there will be an arc. And if we are lucky, the inverter will detect it and switch the current off. But let's do the test. Have it? That's it. You could see a blue spark.
Yep.
And this blue spark was all we've had, which is not a risk for a building. And this mobile device shows us that the arc was detected and interrupted. At this instant, that the current, which is the yellow bar here, was flowing. Then we have this signature, which is caused by the arc. It was detected. We see that because the current goes down to 0.
What do we see on this poster here?
On this poster, we see the results of our inverter test. Actually, we have tested 3 inverters. We see them on my left-hand side. We have tested the Huawei inverter, SolarEdge inverter, and 1 inverter of SMA. This poster shows us the results of these 3 tests. We have in red the current, in blue the voltage, and we see that the current first is constant, then the arc starts, which gives this noise, this signature, which is actually detected by the inverter. And after only about 150 milliseconds, so a fraction of the second, the current is interrupted at this position. The red line goes down to 0, so the current is 0 now. And the voltage in blue, which is the arc voltage over this time where the arc is standing, that goes then to the open circuit voltage of the system.
So, the test is about 3 inverters. But which scenarios have you actually applied?
So we wanted to know how these inverters would actually behave when we have different voltages, different current, different cable length, different positions of the arc in the system. And there are so many variables that we had to define a certain set of settings which we tested. And these settings can be seen here. So we had scenario A, which is a low current setting, scenario B, where we doubled the current to 8.8 amps, and a scenario C, where we had both high current and high voltage of 810 volts.
What would happen if there was no arc fault detection mechanism?
Well, if the arc fault detection mechanism is deactivated and there is a separation in the cable, there will be a standing arc and a lot of energy will actually burn in this arc and the temperatures can get very hot.
How does this look like?
Well, if you want to see that, you should rather protect your eyes with these goggles.
Okay.
But we can test it.
Is that bad?
So the arc fault detection is now deactivated. We still have the same setup as before, and we will now separate the ring from the ball and see if the arc is extinguished or not. I assume it will just be there and burn.
Yeah.
So you see the arc is there standing, it's not extinguished, and it will continue to burn until the sun sets or until we close the contacts.
This graph here also looks very interesting. You see the 3 inverters that were tested, Huawei, SMA and SolarEdge. What else can we see from this graph?
So this graph shows us for the 3 tests, so low current, high current, high voltage, how quickly or how much energy was actually remaining in the arc when the arc fault detection was up and running.
I see here red and blue, so Huawei and SMA, they seem to have good results. SolarEdge is much higher. Does it mean that it's worse?
I wouldn't really say so, because all these 3 inverters are well below the norm. The standard requires us an energy of a maximum of 750 joules, and we see also the SolarEdge inverter is well below 200 joules. What we see is that Huawei and SMA, they have least energy in their arc, but also here we see that the higher the current, the higher the voltage, the more energy is remaining in the arc. SolarEdge has quite a different concept. That explains also why they have more energy in their arcs. And for the SolarEdge concept with our testing facilities, it was not possible to perform test C, therefore we can't see any lines for the SolarEdge inverter.
You already mentioned that cable length is a very important feature. And this graph is about cable length, but what exactly does it show?
Yeah, we have developed this graph and this test to test what performance we can expect when you have really long cables. And we see that the maximum cable length we tested for is almost 2.5 kilometers. And this graph shows us on the y-axis again the energy which was in the arc when we disconnected. We see there's quite a bit more energy than in the test before, but still those arcs which were detected, there the energy is way below 750 joules. What we also see is that there are certain arcs which could not be detected. For the very short cable lengths, all the arcs could be detected. The longer the cable gets, the more arcs were then not detected anymore. So we could say if you have a 2.5 kilometer long cable
every second arc is not detected, but that also means that every second arc is still detected. So it's still a safety feature, and it even works, even if it's not so reliable, in very long cable lengths.
What are typical cable length in PV installations, in residential PV installations?
Yeah, in a normal residential installation, you will not have more than maybe 30, 40, 50 meters of cables. However, in skyscrapers, building integrated photovoltaics, or a large industrial building, you might easily have cable lengths up to 200, 300 meters.
This kind of testing, does it actually allow for localizing the exact spot of the arc fault?
It depends. So certain systems that have so-called optimizers, where the optimizer is a DC-DC converter distributed in the field. And with those systems, for example, the Huawei system, it is actually possible to localize the place where the arc happened. With other systems, like SMA, but also SolarEdge, this function is not available. There, we only know there is an arc, but we don't know exactly where it is.
And is this information helpful?
Yes, I guess it could be helpful. So we have to assume if there is an arc, there is something which has to be repaired. Something was broken, there's a damage. And if we know where the arc is, it just saves time in finding the fault in the system.
My trip to Bern was all about arc faults. In the lab of Professor Christof Bucher, we actually had the chance to check out how arc fault detection mechanisms are upgrading inverters. Different manufacturers go different ways of how to incorporate this new technology into their solutions. Christof compared the different solutions and shared the results with us. Thank you so much for joining me today. It was a real pleasure.